So thank you for coming back. I appreciate your attention, your attendance, and I apologize that we're still coming to you live from my basement, but it's actually for two reasons. One is the cold, which I had seen in advance, and the other is due to an ominous email that was circulated yesterday about the internet being upgraded in our building. So apparently they're just going to take parts of it down and put parts of it back up over the next couple weeks, which made me very afraid for trying to teach in a Zoom environment. So I was already kind of on the fence about whether I was going to go to campus because I was afraid that the Zoomers wouldn't be able to connect reliably or at all. And then it felt like just having the forecast be, negative infinity again for temperature felt like a sign. So we're coming back to the basement here for two good reasons. Do I know how long the internet outage might last? No. A
I'm
schedule
in
might be forthcoming.
I'm in the tech center in Linquist on the north side. The internet's been relatively okay. I haven't noticed anything huge.
Okay, good. That's good to know. Because they said north side specifically, which is where the classroom is, and it's wireless access, which might mean that my computer at the instructor terminal would have internet, but potentially not anyone else's, which is, not ideal. So that's where we're at. Couple of announcements. Let me see here. In terms of your textbook, I just found out that instructors are allowed to ask the library to order books for our classes that they don't have already. Apparently, this is a thing that I had no idea about. So I ordered a copy of our textbook and I posted a link to it on the course webpage, which I'll show you in just a second. The only catch is that only one of you can read it at a time. So get there first would be my recommendation. I'm not sure if it's one of those licenses that allows you to download like chunks at a time. Like sometimes in the library you can print up to like 30 pages at a time as a PDF and read it later. So it is available as a resource. I'm not sure how great of a resource it will be, but I wanted to point that out since I added it to the syllabus. I also updated the printed syllabus with that information as well. Otherwise, the online homework system. Did everybody get a chance to play with that? Looks like most of you had by yesterday. Those of you who haven't seen it before, what did you think? Any reactions?
Yes,
That,
it is a good system. Sorry, Eric.
oh, you can go ahead.
Thank you, Eric. It is a good system, I think, and I could do my homework without any problem. So it is really useful and easy to use.
Good, good. And Eric, you were going to say?
Yeah, I was gonna say the same thing. It was my first time experiencing it, and it was pretty good. I didn't have any issues with that. And what is the most useful part is that it kind of gives you, when you go wrong, gives you the correct one, and you get to know that, hey, I'm not on the right path. So I think it's really helpful.
Yes. So this system was created in an effort basically to clone myself. Because what used to happen is that I would have people do data analysis assignments and result sections, and then I would have to grade them all by hand. And if you got the numbers wrong, you automatically had the wrong interpretations, which was a waste of everyone's time. So in addition to just being more efficient, I feel like this is a way that I can sort of help you remotely, even if I'm not there, by checking your answers against the system. Those of you who've had a chance to do homework this way before, do you have any comments or feedback for those of you, the rest of the class for whom this will be new?
When you're getting wrong answers, always go back and read the paragraph at the beginning of the text, because a lot of times Lisa will tell you what you need to do for things that you forget by the time you get to the computational questions.
Yes, instructions are very important. And if the instructions are unclear, please tell me and I can fix that on the fly. That's just a web page that I can update the text as needed. So I'm happy to make clarifications. We have a comment. I love the system. I say start early so that when question and answers come up about it in the class, you can benefit from it. Yes, start early would always be my recommendation for homework. I have heard from folks in the past that this is a successful way to feel productive, but also procrastinate on other things. So if you're, you have a master's thesis to write or something that's big and amorphous like that, the homework gives you a way to do something that's small and feel good about it, right? Because you see it turn green, you know it's right. And there are very few certainties in graduate school and in life. So I'm glad that this can be one, at least. All right. Any other questions about doing homework this way? No? Okay. If you were not able to log in, please let me know immediately, because that's why we're doing this homework 0, so that you can each get a chance to test the system and I can make sure that everyone knows how to access it and submit their responses. That's the key. And I will let you know when homework 1 is available. It's not going to be for several weeks. Let me look at the syllabus here. The 7th of February. So the first homework is going to be a review of linear models, which is what we are going to be talking about this week. So hopefully some familiar stuff, but some unfamiliar stuff potentially too, depending on what you had been asked to do in previous courses on linear models. So shall we start the screen share? Start the show? Well, while I get that started, let me get the transcript started as well. There we go. Get my annoying words in front of me. And now I'm going to hide it for myself. We're going to share. There we go. Who can see this transcript? Hopefully anybody who wants to. Participants can now see your screen. Yes, that is the point of sharing. Thank you. I love the human factors that are in here. Hide floating meeting controls. There we go. So this was the web page I wanted to point out that I had updated down here where the textbook is. There is a link to where you can look at the book on the library. So that was what I wanted to say about that. And we have 2 PowerPoints open. It was this one that we were in. So what do you remember from last time?
I had a quick question actually about
Let's do that instead.
time
Yeah,
material, if that's okay.
that's absolutely okay.
So when we're referring to maximum likelihood, when you bootstrap to find parameter estimates, is that finding maximum likelihood, like the highest point on that bootstrap curve?
Not exactly.
Okay.
So bootstrapping is sampling with replacement from your data and re-estimating the model on each subsequent new sample to see how variable your results would be, how idiosyncratic they would be to the particular individuals that were sampled. And it is generally used as a way to get standard errors or confidence intervals around a slope or a parameter estimate more generally that are less susceptible to violations of assumptions than standard errors that show up using off-the-shelf formulae. So I can see why you would put them together in your head, because they're both iterative processes, meaning you do the same thing over and over, but maximum likelihood comes eventually to one solution that is most likely. And so there's only one answer. Whereas in bootstrapping, there is an answer for every single resample that you build. Does that help?
Yeah. Yep.
Cool.
Can I ask a question about that real quick?
Yeah.
About the bootstrapping, does it make it less susceptible to the, just because you're trying more different options, or is there a different reason it makes it less susceptible?
So I'd say there's 2 sort of general ways that you can arrive at a standard error. Mm-hmm. One is model-based, meaning like asymptotically, like in the best case scenario where you have lots of people and everything works out like it's supposed to, this is what the standard error should be. Mm-hmm. And the other way is to find it by brute force through some kind of resampling, which is what bootstrapping is. I think jackknifing falls into this category, maybe permutation tests. That's not something I know a lot about, but I think it's still the same kind of idea. Yeah, so at the end of the day, what a standard error is supposed to mean, and we will actually talk about this in more detail in this next unit, it's supposed to be an approximation of the standard deviation of the sampling distribution of a statistic. I know that's
so it's just because it gives you like more different variations of it, so the final one's going to be more complete then?
You get more variations on what the estimate could be. You're trying to mimic the sampling distribution using your own sample.
Mm-hmm.
And so then the range across, like you can build, say, a 95% confidence interval. That's what a standard error would normally be used to do. You can actually see, like, line up all your results and see
Okay.
where 2.5% on this side and 2.5% on this side is.
Okay. I just, for some reason, I was thinking would like make it less accurate, not more accurate. So I was just, I needed to like work it out in my head. So
I think if you have enough people and all of your assumptions hold, they should converge onto the same answer.
Mhm.
But if those things are not true, then I think bootstrapping may give you a more realistic answer, particularly if you have outliers and you're concerned about those outliers having undue influence or leverage on the solution.
yeah, that makes
Bootstrapping
sense.
is also used in circumstances where standard error approaches fail. Indirect effects in mediation models is one example, and then for certain statistics that just don't have a known sampling distribution, like the median in some cases. When we get to quantile regression, for instance, the only way to get standard errors out of that is through resampling, bootstrapping. Because there's no formula, because it's maximizing an absolute value, which is a pointy phenomenon as opposed to a curved phenomenon. But
Awesome. Thank you. I appreciate it.
sure, more detail than you wanted to know. I think my caffeine just kicked in. I think that's what happened here. So I'm going to push the can away, pick up my water bottle instead, and ask if anyone else wants to talk about anything from last time or otherwise.
So I don't know if this may be just because I don't have a ton of knowledge in IRT yet, but in our IRT course that we took last night, we were talking about measurement of the error of the true score, and like how, when we're measuring latent traits, that they're not directly measurable. So when we're talking about generalized linear models and it's based on, violating the assumptions of normal distribution of error, but the error isn't measurable, then how would generalized, this might just be me going off on a completely wrong track because I don't have all the vocabulary down yet, but do you know what I'm getting at?
I think you might be mixing apples and oranges a bit, because in item response theory models, so that's what IRT stands for, and the same is true in any latent trait model, so confirmatory factor analysis, structural equation models, that whole world where you're working with latent variables, they're not real.
Okay.
And that's the problem, is that you're trying at the end of the day to nail down a score on something that isn't real. And so the considerations in that are different, I think, versus the considerations of how you get results that are trustworthy when you have all the information. So in this class, we're going to have observed variables as predictors, whereas in that class, the latent variable is the predictor. Okay.
It just seemed very like we're basing all this knowledge off of things that we don't even know are real, and that which I'm sure I'll learn more about it later on, but it just kind of made me question some things a little bit.
It's the latent score itself is not real, but the where it comes from is real.
Okay.
Basically what you're doing is you're taking all of the relationships among the responses and test items in that case, and that covariance, essentially that relationship, you're putting a name on it, and you're turning it into a new variable. So the covariance is real, but the thing that's created from it is not observed directly.
So we would be applying like the generalized linear models, like that theory to the observed, whatever, the observed results, as opposed to like the true score or.
Yeah. Okay. We got all the information we need in this class.
Okay.
But to prepare you for things where you have latent variables, then that's what this class has sort of some fundamental ideas that help you then transition to those classes, which is why if anyone's planning on taking SEM, this class will help you get through that much more easily. Okay, so we're having some folks having some technical difficulties. If you get disconnected at any point, come back into the meeting and I'll let you in. I have my participants window and the chat window open so that I can see if there's anybody in the waiting room. So yeah, we kind of hit everything that's on this slide, actually. Random effects and latent variables are additional Legos that we will be adding. We talked about a little bit about estimation and a little bit about link functions last time. So linear models is what you already know. You learned them in the context of predicting a quantitative outcome whose residuals are supposed to be independent, normally distributed, and have constant variance. Everything that you're going to do in this class up until we hit multivariate models is still for independent observations. But we're changing the assumptions of the model to better fit the data for outcomes that are not continuous variables. And the way that we can do that, this is slide 26 here, is through the magic of maximum likelihood. So we are switching out the formula that we use to measure height with to a distribution besides normal that's a better fit for what the outcome residuals could possibly be, or what the conditional distribution is called. That's what we would say. And so I skipped around a little bit, and I want to make sure that we hit the slides that I skipped. So we can start with, let's see, this one. It's 27. So any other questions before we dive back in? No, we're ready? All right, then away we go. So what's so great about normal? The reason that you are taught in general linear models that the residuals have to be this way is because that is the formula you're using for height. So minimizing the sum of squared residuals is how you determine what the best answers are for your intercept and slope fixed effects. Minimizing the sum of squared residuals is the same thing as maximizing the likelihood. The residual likelihood in particular for these sorts of models, but it's analogous. So it's kind of like saying that, well, I ordered a cheese pizza and I assume that it's vegetarian. Well, yeah, because I ordered cheese pizza and cheese is vegetarian. So true story. Oftentimes we order pizza here from Falbo's. Anybody Falbo's fans in the house? No? Well, they have a particular pizza that is mac and cheese on a pizza. Macaroni and cheese on a pizza without the traditional red sauce. It's a different, like a cheese sauce. It's quite excellent. But then they go and ruin it by putting bacon on it, in my opinion. I hate bacon. My son hates bacon. So there have been times where they have screwed up our order and put bacon on it. And if I take off all the bacon, maybe technically it's vegetarian, but you can still kind of taste the bacon and it's ruined. So you can think of the idea of like doing transformations to your outcome variable to make it more normal, like picking the pepperoni and the bacon off the pizza. Like it's a workaround if you have to, but there's got to be a better way. Make the pizza the way you wanted to order it in the first place. So if you order a general linear model, then you have purchased residuals that are independent, normally distributed, and with constant variance. So if that's not going to fit, if you're hungry for something else, order something else. So that's what we'll do. Link functions, then, is the other piece of it that we have to add to our order. So here is some vocabulary for how I am going to talk about different types of variables as outcomes. This is related to levels of measurement, but this is more of a how would you approach a model for them kind of perspective. Big difference is categorical versus quantitative. Within categorical, these are the kinds that we'll talk about. So there's binary, which is just there or not, otherwise known as dichotomous. Nominal, which is 3 or more categories, but they are not ordered. So for instance, favorite type of pet. Of course, the correct answer is cat. But some of you, I suspect, would feel differently. The correct answer is dog, or the correct answer is guinea pig, or fish, or what have you. Point is, we would not agree. So it's just different kinds of something as opposed to any kind of scaling. Ordinal is a tricky one. So this is categorical data, but the categories are undeniably ordered. So a Likert scale, by the way, if you have 1 equals strongly disagree, 2 equals disagree, and so forth, you won't have to convince anybody that strongly agree is a more positive opinion about something than disagree. but it's the distances between them. Like, can you really say that the difference between 1 and 2 is the same with respect to whatever you're measuring as the distance between 2 and 3 and 3 and 4? Not really. You might want to pretend, but not really. By the way, for those of you in IRT, this will be called polytomous data eventually. They have nominal IRT models and they have ordinal IRT models that go by the name graded response or partial credit. We'll talk more about those later on, but just to draw the tie between there. Synonyms for categorical that you will come across from myself and other people: discrete variables, qualitative variables, factor variables in R are this way, class variables in SAS, or grouping variable. So in your head, when you think categorical variable, think kinds. And then the question is, are the kinds ordered or not, basically? If it's binary, then it doesn't matter whether it's ordered or not because there's only one difference. And so you don't have to assume equal differences because there's only one to worry about. So this is the first part of what we're going to cover this semester, starting with binary. All right, quantitative. So there are quantitative variables that are bounded and there are quantitative variables that are not bounded. And this is a distinction that in general linear models often sort of gets like shoved under the rug. A lot of times people use quantitative variables with boundaries to illustrate something, but I'm going to show you the proper way to analyze these variables instead. So for instance, binomial type variables. If you have something like the number correct on a test out of so many, that is an example of a quantitative variable. If you have 2 answers correct, that's twice as much as 1. I mean, that there's an interval scale that actually means something. But it is bounded by a known low and a known high. So the worst that you can do is get no answers correct. The best you can do is get all of them correct. So binomial type data is often skewed data because people push up against the boundaries of 0 or 1 if it's a proportion, or 0 or 100 if it's a percentage. Count variables have 1 boundary instead of 2. So for instance, number of cigarettes that you smoked at a given day. The fewest number of cigarettes that you can smoke is 0. And the highest number you can smoke in any day, I don't know, but it's probably a lot, right? There's no upper end to it. So in this case, you would have to make sure that your model understands that no matter how low you are on the predictors, you cannot predict fewer than 0 cigarettes per day. So the job of the link function is to rein it in one direction. Just as an FYI, this we'll talk about later, but count variables have special cases involving lack of zeros or extra zeros. If a count variable doesn't have any zeros, it's 0 truncated. So that can happen, for instance, if, let's say that you're looking at number of infections amongst hospital patients, and you get a data set from a hospital. Well, by definition, like everybody who is in your data set has been in the hospital at least once, or they wouldn't be in the data. So like if you were looking at, number of days in the hospital or number of visits to the hospital, the lowest you have is 1. Turns out you need a special distribution that understands that 0 is not possible. It's 0 truncated. If you are mixing populations together of people who just don't have something versus people that do. So for instance, if you asked both smokers and non-smokers, how many cigarettes did you smoke today? You're probably going to have a giant pile of zeros because all the non-smokers will have said that. And that type of distribution is known as 0 inflated, meaning there's more zeros there would be expected from just a regular count process. And there's models for that as well. Okay, with me so far? Okay, so those are the kinds of variables that we're going to be predicting this semester. Things that are either categories, counts, or numbers, but that are not continuous. Oh, thank you for the yellow thumbs. I appreciate that. So then how do we change the model to accommodate these different kinds of outcomes? So this is the part that we skipped last time, and you will see this over and over again throughout the semester with more specifics, but I just want to plant the general idea in your head as to how this works. Generalized linear models have three parts. First is the link function. How do you transform the conditional mean to be predicted into something that is actually continuous so that it can be predicted by a linear model? Then you can have your regular old linear model. Intercepts, slopes, interpreted the way that you're used to. It's just that they're predicting not the original variable, but a transformation of it that happens as part of the model. So link functions are not about transforming data. We don't do anything to the data in the data set. The transformation happens within the model itself. And then the third part of it is, okay, so if the residuals aren't normal with constant variance, what are my other choices? Well, turns out there's a whole bunch of distributions that you can choose from that will be much better matches to data outcomes of these particular kinds. So this is the slide we looked at last time. The idea, for instance, of a binary variable. If you can only have a 0 or a 1, what you're actually trying to predict with your linear model is the probability of a 1, because that's the mean to be predicted. If you try to do that with a continuous quantitative predictor here, the model doesn't understand, unless you tell it specifically, unless you order it that way, that no matter how high somebody is on X, their prediction should not go past 1. The probability of a 1 at 1 is the highest you can have. And likewise, your prediction can't go past 0 on the other side. So the way that we fix it is to create a bendy line that looks like this, otherwise known as a logistic curve, and that occurs through this thing right here, which is a logit link function. I would also accept the words logit. I had an argument with a grad student once about this, and he had a very good point. Because you don't take the log, you take the log. So it's the logit. Fair. Okay, I'll do that. So this is, I pronounce it logit, but however you want to pronounce it. What it is you take the probability of a 1, you divide by the probability of a 0. That part is odds. We'll talk about this in detail in the next unit, unit 2. And then you take the natural log of that thing. The logit is a metric that goes on forever and ever. It's symmetric about 0. So a probability of 50-50 is a logit of 0. And it goes on from positive to negative infinity. So your regular old linear model then predicts the logit. When you back translate it, what's known as an inverse link function, or what I would informally say, if you unlogit it, the probability stays in these boundaries like it's supposed to. We have a comment, GIF versus GIF. Yeah, I'm not sure which is correct. Is there an actual answer? Both correct. Okay.
I don't think there's an actual answer. That's just like an example where people get pronunciations different.
Tomato, tomato, potato, potato. Aunt or aunt is another one. So Jonathan always says aunt, which to me just sounds weird. But anywho, it's logit to me. It's the log of the odds of the probability of a 1. And what it's for is to translate what is being predicted into something that has no boundaries. When you back translate it, it observes the boundaries it's supposed to. Likewise, for count data, the link function that we will use is the natural log, because the natural log makes a count unbounded in both directions. So there's relatively few different link functions to be learned. Logit is by far the most common, and log. So there's variations on this that have to do with asymmetry of prediction. We'll talk about those later, but this is pretty common. All right. Questions?
Yeah, can I just clarify what we talked about?
Yeah.
Okay, so this link function, it transforms, it's something within, we add on to the linear model, right? And it transforms the outcome into something new, our outcome of interest. And then the linear model does the same thing it does to like regular outcomes to this new outcome.
That is correct, except that I would say the link function is operating not on the outcome, but the conditional mean of the outcome.
Okay.
It's a subtle distinction, but what I mean to say is you're not doing anything to your data. Your data stays zeros and ones. Inside the machinery of the model, you say link equals logit, and then it understands that instead of predicting the probability of a 1, it's going to predict the logit of the probability of a 1.
All right.
But otherwise, yes. And the purpose of that is to create a new outcome variable for the model that is unbounded. Then you got your regular old
Okay.
linear model.
All right. Okay.
Does that help?
And can you talk about how that conditional mean part again? I mean, the linear model does predict the conditional mean. I remember. Is that the same thing you were talking about? The previous one?
The linear model predicts the link transformed conditional mean.
Oh, okay. So same thing, except now it's like the link transform thingy.
Yep. It's a change in vocabulary, and it's a change in the scale of the parameter estimates. So you might have a fixed intercept in logits of 2. And you're like, okay, what the hell is that? And the only way to answer that question is to back translate what 2 means into probability, which is somewhere in the 80s, I think, 0.8-ish, somewhere in there. I don't have that part memorized. What I do know is that in positive, a positive logit corresponds to a probability above 50-50, and a negative logit corresponds to a probability below 50-50. That's what I can tell you off the top of my head.
Got it. Okay. And the whole reason we're transforming is so that, well, if we were to just use the regular linear model, general linear model on our untransformed outcome, it's going to get out of bounds. So we're going to get probabilities like above 1 or below 0. Then we transform it so it stays in bounds.
Yep. That's exactly right. Yep. If I took my binary data and I fit a regular general linear model regression to it, the model would be this picture on the left here. It would keep predicting probabilities above 1 or below 0.
Got it. Okay, thank you.
Yep, thanks for the questions. And the let me say it my way, that's very helpful, I think. Yes, and others agree, so I can see people nodding, so it's not just you. All right, anyone else while we're on the slide? Okay, so we're going to go over this in a lot more detail because the translation of logits to odds to probabilities is tricky and easily screwed up. So my job is to help you, to prevent you from screwing it up. That's our goal here. But this is just to give you an idea of what's going to happen. So the logit link function solves the problem that a linear model creates predicted outcomes that go out of bounds. That's that part. The other part of it is about the distribution that's assumed for the residuals, that they're normally distributed with constant variance. And if we get that wrong, then we can't trust the standard errors for our parameters. If we can't trust the standard errors, then we can't trust the t-test statistics, and then we can't trust the p-values. So that's the other part that we got to solve. And so rather than use the normal distribution as our way of computing height for what parameter set is best for our data, we're going to pick a different one. Here's Bernoulli. It's always capitalized because it's some dude's name. The Bernoulli distribution is the simplest one that I've ever seen. The height is the probability of a 1, if that's what you got, times the probability of a 0, if that's what you got. That's it. So there's only, for each person, 2 possible values for how tall each person's data can be. And in binary data, rather than assuming that we have constant variance, there is no separately estimated parameter for variance. It turns out that normal distribution is one of the few that has a separate parameter for mean and a separate parameter for variance. In many other distributions, they're linked together in a particular way. So Bernoulli has one parameter, the mean. Because if I know the mean, meaning the proportion of outcomes that are a 1, I know what proportion of outcomes were a 0 because they got a sum to 1. So the variance is a function of the mean. It's the proportion of 1s times the proportion of 0s. And skewness is given by those 2 values as well. So it works out like this. If you have a data set, let's just go unconditional here, where it's 50-50 with respect to the split of zeros and ones, that data set, that variable, has a variance of 0.25, the end. You know that. The further you go from that even split, the less variance you have. To the point where if everybody has a 1, then you do not have a variable, you have a constant. So what I'm trying to say here is that in a Bernoulli distribution, variance is not really a thing. It's not a thing that you have to estimate. It is controlled by the mean and it is non-constant. So by specifying Bernoulli, we are assuming something different about the residuals, that they follow this distribution instead of normal. And there's others. So here are the combinations of purple is the link function, and the second part in the blue is the conditional distribution that these things go with. So for binary data, we're going to pair a logit link with the Bernoulli distribution. That combination, by the way, is known to the rest of the world as logistic regression. So think of it this way. If you're sitting at an Italian restaurant and you order fettuccine alfredo, right? There's probably a picture of it. It looks good. You don't care that there's 1,000 grams of fat in it because you're going out to dinner and you're having a good time. But if you go back to the kitchen, right, how would you convey to a cook what's in fettuccine alfredo? Okay, well, I need 9 ounces of the fettuccine pasta. I need X amount of cream sauce. I need X amount of mushrooms. I need X amount of whatever, right? What are the ingredients that make fettuccine alfredo? So the way that I'm approaching this is, what are the ingredients that create a model by this name? So logistic regression is this combination of ingredients, a logit link and a Bernoulli distribution. If you've heard of probit regression, that's a probit link, which is on a different scale than logits but does the exact same thing, plus a Bernoulli distribution. Probit is also known as ogive in the IRT world, by the way. That will be coming later. If I have ordinal or nominal data, that's some kind of logit link. So either cumulative logit for ordinal or a different kind of logit for nominal, plus a multinomial distribution. Multinomial is a generalization of Bernoulli for more than 2 categories, but it's a categorical distribution that works the same way, doesn't have a separate variance. This combination for nominal data is often called multinomial regression. It's named for the distribution rather than the link for reasons that are unclear to me. The ordinal version is often known as a proportional odds model because it invokes an assumption as part of it that I'll talk to you about later. So each of these things has a name that people will call it, but to be absolutely clear, I would use both the name and describe the ingredients. That way, if somebody is reading your paper who isn't familiar with the way these things are named, they can still hopefully follow what you're doing. Likewise, if you have a proportion correct or something like that, anything that has floor or ceiling effects, then that's going to be a logit because proportions are bounded between 0 and 1, but a binomial distribution. Bimodal data, that's a logit plus a beta. That's a hard one. Counts, that's a log link function instead of a logit plus a Poisson. So that's French for fish. I know that one. But it's a distribution where the variance and the mean are equal. So as the mean increases, the variance increases. So it has like a fan spread to its predictions. If you have extra skewness in your count, then we'll pick up negative binomial instead. This is another one that goes by negative binomial regression as opposed to Poisson regression or count regression. If you have a continuous variable, something like response time or like minutes of exercise per day, something where you're going to have some skewness with a long tail, you can use either a log normal or a gamma distribution with a log link so that you don't have a boundary at 0. And then zero inflated has these kinds too. So this is the first half of this class to go through all of these possibilities. But they all work in the same way. A link
Lisa?
to create something that is continuous and a distribution that better matches the data. Question?
Yes, I have 2 questions actually.
Yes.
First of all, so we should select the link function based on the distribution of the residuals of the outcome variable. But
Not quite. Not quite. Close, but not quite. I would say you select the link based on what are the possible values of the outcome and whether they're bounded. So basically, do you need to unbound it in one direction or two?
okay, but can we use any kind of variable as explanatory variables?
Yes.
No? We do not have restriction in the explanatory variables.
Correct. Any kind of predictor.
Okay, and my second question is, so when we identify the kind of the kind of distribution that the possible values of the outcome variable has, can we change the link function? For example, if I know that the possible values of my outcome variable, it follows a cone distribution or a Poisson distribution. Should I use the log link function, or can I use another one?
Log is by far the most common. I think there is an inverse something that sometimes gets used, but that one's really tricky because it's 1 over as the link, which is all screwy. The textbook has more choices that they mention. So there are more choices than just this. This is sort of like the most common.
Okay.
These
thank you,
are
Lisa.
the ones that tend to be paired together, is the way I would say it. Okay. Other questions?
Do you have a favorite?
Do I have a favorite?
Yeah, out of this list.
Do I have a favorite? Boy. No.
Sometimes people make us, connotations with certain things. It's like fun memories of using one over the other.
I have some that I hate more than others. Can I say that? I have a least favorite.
Sure.
Beta is a nightmare. The beta distribution has shape and scale parameters that, like, there's 18 different ways to set it up based on who you're reading and which software you're in, and it becomes very tricky to get back and forth across them. The same is true if you try to go from binomial to negative binomial. It's very tricky to do that. And also for ordinal data, I kind of hate proportional odds models, even though they're the most common, because they make the assumption that the slope is the same regardless of whether you're predicting the transition from 1 to 2 or 2 to 3 or 3 to 4 or 4 to 5. And so I'll show you how to not do that. I'll show you how to actually test that assumption. So, yeah. So this is sort of like our list of what we'll go through. And then the second half of the class is expanding what we're doing to predict more than one outcome at a time. So not just single outcomes, but multiple outcomes. So in multivariate models for things like mediation, multivariate models for repeated measures, for dyadic data, stuff like that. And that will end up in path analysis. All right, let's see. Same predictive model. So Vladimir, to your point, you can have any kind of explanatory predictor variables that you want, and they do not have different names. So that whole thing, like ANOVA is for categorical predictors and regression is for quantitative predictors, like that kind of distinction does not happen anymore. There's no special names. You can put whatever x's you want because x's do not have distributional assumptions. You don't assume anything about the x's. You can do whatever you want for an x. The other part is that when we talk about slopes, for instance, you're used to thinking about a slope as the change in y for a 1 unit change in x. You have to catch yourself and say it's the change in linked y. So it's the change in logit y, or it's the change in log y for a 1 unit change in x. After you make that switch, you can talk about the fixed effects in the same way that you normally would. We're still going to have t-test statistics for individual slopes. We're still going to have f-tests for groups of slopes. They're just not going to come out through sums of squares. So you're not going to see sums of squares model and sums of squares residual and sums of squares total. That's all gone for generalized models. You won't see that as part of a summary. You can still get the f-tests that tell you the same things though, and I'll show you how to do that. And the other part of it is whether or not you end up with t or z or chi-square versus f is going to differ by software. So there are some inconsistencies in the choices that are available for those things. And I try to make it consistent across programs as much as possible. But there may be places where you end up with an f from one program and a chi-square instead for the other. The difference between them is whether or not you use denominator degrees of freedom. So if you are testing one thing with denominator degrees of freedom, which means you're controlling for sample size and the complexity of the model, that's a T. If you are not using denominator degrees of freedom, that's a Z. Likewise, if you are testing more than one slope at a time, such as testing whether or not the R-square for the model is significant, that's an F if you use denominator degrees of freedom. If you do not, it's a chi-square. So there will be a little bit of inconsistency in the p-values that show up as a function of this because of whether or not the software is using denominator degrees of freedom. So just be ready for that. And I think there's one more. Yep. R-square is gone. That's the other thing. Because a variable with a conditional normal distribution has a separately estimated variance, we would commonly refer to the amount of variance that's accounted for as R-square as an effect size for the model. But let's say we're predicting a binary variable. Do binary variables have separately estimated variances? Nope. And more than that, the variance is not constant. It depends on where you are on the prediction line. So we can't watch how much the variance is decreased by adding predictors because the variance doesn't change. So the way that we'll have to indicate effect size is not using R-square and using different things. People have tried to develop analogous R-square measures for generalized linear models. They do not agree whatsoever. You can get widely different answers based on whose R-square you're using. So anytime that I see something like that, like, no, we're not going to do that. What do we use for effect size? Oh, it depends on the model. In logit land, you're going to use odds ratios. In log count land, you're going to use risk ratios. You can always take your t-test statistic and back translate it into an R effect size or a D effect size. So that's one way to do it that's pretty easy. It's just that trying to come up with an overall sort of model goodness via R-square is not going to be possible. So those are the big differences that we'll see. All right, history of generalized linear models. So things that are still out there that you may come across, data transformations, for instance. I have a great example that I'm going to show you that is a count variable. And the only reason that I ever had that data set cross my path is because the student asked me for a transformation that would make the data more normal. And I looked at her data and I went, yeah, no. That there is no way that you can take a pile of zeros and transform it into something that looks more normal. That is not possible. Here's what you should do instead. So that's one of the examples that I'll show you this semester. Back in the day, there were different kinds of transformations that people would do to the outcome, either to extend it into something that's unbounded or to try to stabilize its variance. And so these are sort of last resorts at this point. Occasionally, I might recommend something like this, but only in particular situations such as very small samples or a whole lot of repeated measures that can't be adequately addressed with maximum likelihood. And also non-parametrics. So non-parametric statistics are often introduced as ways to still do general linear models that have fewer assumptions, but in reality, they actually have more assumptions. You need a class on non-parametrics like you need a class on VCR programming, is what I would say. And for those of you who don't know what a VCR is, exactly. It used to be something, if you wanted to record a TV show in the 80s or 90s, you had to get a special machine and you had to program it to turn on and to tape your TV show, because they were tapes. And it was very complicated. And now we have Hulu, and this is not even a thing. So we're not going to worry about those either. And then multivariate models is where we're headed, and once we get a chance to go through all of this list of possibilities. And so here are some instances in which you would use multivariate models when you have repeated measures, or you have dyadic or family data, or when you have more than one outcome at a time, and you have questions about differences in effect size. So let's say that you are planning an intervention study designed to reduce negative outcomes, and you want to know if your intervention has a bigger effect on reducing depression than it does on reducing anxiety. That could be a research question, right? That requires a multivariate model, because you would have to predict depression and predict anxiety at the same time in order to compare the size of their slopes. So we will do that later on in the semester. And indirect effects and mediation, which is a thing. There. So that's where we're going to end up. No more ordinary least squares. Everything's in maximum likelihood. And when we get to path models, multivariate models, we're going to have to switch software to some extent. I need to play around with R more to see what the distinct possibilities are. But I have a hunch that not everything will be able to be done in every package the way that I want. But I'll cross that bridge later this semester. And so, wrapping this lecture up then, what we're going to do, this course will help you better understand linear models. So all of the things that you've learned in regression and ANOVA classes, you're going to get lots of practice doing. So we'll be doing the same sort of thing over and over again with respect to the X side. It's the Y side that will be changing out depending on what kind of outcome that we're predicting. Link functions to predict any kind of outcome, and the use of maximum likelihood estimation, including how we look at differences in log likelihood to judge improvements to the model. And this material is useful in and of itself because odds are good you're going to come across an outcome that's not normally distributed and you need to be able to predict it. And because all of these are prerequisite skills for future courses. So the material that we'll cover in this course will be directly relevant to learning multi-level or mixed effects models, which is 6271 or 6272. There's two variants being offered, at least in this department: factor analysis and structural equation models, as well as item response models, and I've got the classes for that. Factor analysis and structural equation models is going to be offered this fall. I think I'm also planning on doing longitudinal again this fall. So that will be good to have this course first if you want to have any of those other courses. And for those of you who've already been through some of the other courses, you may find yourselves going, oh, that's what she was talking about. Oh, okay, I get it now. All right, the end. So, any questions on any